Right. Hello, everybody. Thomas Dimitrovich here, and it is Friday. It's Q&A Friday, and I had one question that came in. I know I saw it. I got to find it. That was on. It was related to a previous topic or a previous presentation that I did on selective coordination. I think it was on selective coordination. It was somewhere in there we were talking selective coordination. And I showed two curves, and then I walked through the selective coordination tables. I think that's where it was at. It was on the selective coordination tables. And I'm just going to go to my YouTube studio and look at comments. So, and it's at the beginning of a long weekend. It's the beginning of a long weekend. So I hope everybody has some cool plans out there for the weekend. I know you probably do. Cutting grass, maybe cutting some hedges, shoveling something, or something of that nature. I know it's work related, but just got to take it easy. Whoops. All right. So, hello, Mr. Dimitrovich. All right. So I'm just looking through some of the comments. Okay. All right, so this was, I can't pronounce the name, and it was on my selective coordination tables session. So if you go out to my, I did a session on how to use the tables, and I have a set of curves right here. All right, so I show these two curves, and I'll tell you what, every selective coordination discussion I have, I'll give you the story behind this and how I use this. I'll give you how I use it, not how I came up with the idea. I go out to a location, I believe it was in California, and I'm talking to consultants, and I'm doing one of the topics that they wanted me to talk about was selective coordination. So I go in to see the consultant on selective coordination to talk about selective coordination. He brings his team in, and it's this relatively small office, and there's a lot of people around the table there. And the person who's in charge says, "Hey," he says, "Look, we do selective coordination for a living. This is what we do on a daily basis. We do coordination studies, short circuit studies, and arc flash studies. I don't need you to tell me what selective coordination is." He says, "I need you to tell me how you're going to save me time and save me money and get me out of jams." And I said, "Okay." I said, "I'll do that on one condition. You answer a quiz question." And he agreed. And what I do is I show these curves. And my question is, do these selectively coordinate? And the way I do the deal with whoever it is I'm presenting to, I tell them, if you get this answer correct, if you get this question, if you answer this question correctly, I'm not going to walk through what selective coordination is because you know what you're doing, in my opinion, at least on the front end, because a lot of people get this question wrong. And if you get it correctly, then I'll go in and help you understand how I can help save you time and save you money in engineering a system that selectively coordinates and addresses incident energy that selective coordination can cause. So, the question I always pose is, do these two circuit breakers, an F150 upstream of a BAB20, do they selectively coordinate? That's the question I pose. That is what I'm looking for. So I gotta log in over here. In that meeting, what was really interesting was that individual has a group of people sitting around the table, and I drew these two. I didn't have my slide deck. I didn't have my computer out of my bag because we were just filing in and everybody was sitting down. And he says, look, I don't need you to waste my time. I know what selective coordination is. I know how to do it. We do it for a living. I need you to tell me how to save money and time. And I didn't even pull my computer out yet. I said, okay. And I drew these two curves up on the whiteboard. I said, you answer this quiz question. Do these selectively coordinate? And the whole group around that table was sitting there and they were looking at it. The youngest guy, it was a guy, and it was a very young individual. Looks like he was probably right out of college. And he raised his hand and he said, you didn't give me enough information. I said, what are you missing? He goes, I need to know what the fault current is to be able to tell you if those two circuit breakers selectively coordinate. And my jaw dropped because he got it right. That was the right answer. The answer was that I didn't tell you what the fault current was. That you can't tell whether or not two devices selectively coordinate unless you know the fault current that is passing through both of them. I immediately opened up a catalog and we did the entire discussion. I did not use my slides at all. We worked on a whiteboard. We drew a one-line diagram and we basically walked through selective coordination, all the different types of configurations and how to address meeting the needs of the National Electrical Code, but forget about that for now. I mean, what these people were involved with were designs for reliability. And that is what selective coordination is about. Hey, Christopher, happy Friday, brother. So that customer was, and I tell you what, I never had a more. And I remember that day, and it was, I don't know how many years ago, 5 years ago, something like that, maybe more. I'll never forget that day because it was one of those discussions where we had an entire room of individuals, and I would say there was probably, it was like maybe 5 guys over here, 5 over here, and 2 of the heads, so about 12 people. And everybody was engaged. And there were no PowerPoints. It was nothing but a whiteboard, and we were drawing one-line diagrams, and we were trying to understand selective coordination, solving a bunch of issues. They brought a couple jobs up. They drew a one-line diagram. They said, this is a problem. How do I address that? We talked about mixing manufacturers and all that jazz. And it all started with, do these selectively coordinate? So when I looked at the chat off of my YouTube site, and here's the message on this. When the fault current gets above 1500 amps for this pair, F150, the breaker, not the truck, BAB20, and I believe it'll go up to a BAB30. When you have those two breakers in series with each other and you run fault current, the moment you get above 1500 amps, they'll both open. Guaranteed. I mean, we've proven it in a lab. And this is just, from an Eaton perspective, Siemens, GE, Square D. I mean, you put current through those two breakers, similar sized breakers, similar looking curves. They're both going to open above around 1500 amps. And 1500 amps is right in the sweet spot of that blue trip curve, the upstream breaker. So the question that came in from one of my viewers was, and I get this question a lot, and that's why I honed in on it. What happens if my fault current is greater than 1500 amps, Tom? How do I address the problem? Now, what I told you was the goal of that session that I did, and it's check my YouTube channel up. You'll find it. It's one of my most viewed videos. on how to interpret the selective coordination tables. And I had one for breakers and I have one for fuses. And I'm addressing just helping you understand what to do, how to use the tables to when your fault currents are high enough. And I just talked the tables because that's what that's about. But let's say that the tables tell you 1500 amps and you've got 5000 amps of available fault current. What do you do to address this, to address selective coordination? So here are a couple ways to solve the problem. One, you can take that that F150, you can focus on the upstream device to make it go slower. I mean, that's basically what you want to do. You want that circuit breaker to hold its contacts closed long enough so that the downstream circuit breaker clears the fault and the upstream circuit breaker keeps its contacts closed. And you don't want chatter. You don't want those contacts to do this, because what happens when you get this going on, it will create dimples. Dimples look good on you and me, but they don't look good on breaker contacts. Walter Gonzalez, you know what? I do now have a plan to discuss examples for generator overcurrent protection. It's amazing how your comment can just generate that. So let's do this. I'm going to put a note. I will put together a program on generator. I'm just taking a note. Generator overcurrent protection. Overcurrent protection. All right. Overcurrent protection. And in generators, that's an interesting point. So I will definitely do that. Thanks for the thing. Hey, Ryan Jackson in the house. Okay, so what do I do to solve? What do I do if I've got, let's say, 5,000 amps and I've got this problem going on? You got a couple options. A, you can focus on the upstream device, that F150, the circuit breaker, not the truck. You can make a larger device because the problem is the instantaneous, right? So as the fault currents go higher, you're into the instantaneous regions of both the downstream and the upstream device. So they're both gonna go. So what you want is that upstream device to hold its contacts closed. And I can do that by putting a beefier device whenever you want a circuit breaker to put pressure on a set of contacts for high fault currents. What you don't want, you want enough pressure on those contacts. How do I get pressure on a contact? Think about a circuit breaker. What's inside of a circuit breaker? You've got springs, you've got a set of contacts, you've got contact surfaces, you've got metal that's pushing a lever down to hold the contacts to get together, and during fault conditions, what's the other thing you've got going on? You've got flux, you've got magnetic forces that want to push those contacts apart. So to hold those contacts closed, I need pressure, physical pressure. How do I do that? I do that with springs. I do that with beefing up the levers, beefing up the hinges. Right? There's hinges in there that for that contact's got to rotate. I have conductors that have to hold that mount on those hinges. So if I make the metal bigger, I need to think about that little flexible cord that's inside it, that little flexible, I don't want to call it a cord, little flexible copper braided conductor that connects that arm with the heating element. So, hey, thanks, Walter. So what happens is everything gets beefier, right? Meanwhile, the breaker's getting bigger because I've got to hold those contacts closed. And I don't want chatter. I don't want dimples. So I have now 5,000 amps, not 1,000 amps or 800 amps that I've got to hold these contacts closed for. So I need to bring more beef. And what that does, it makes the circuit breaker larger. So I might have to go instead of to say 150 amp device, I might have to go to a 400 amp frame and dial it down to say, if I can get it to 150 amps. So what does the frame do? When I build a frame, I go from a smaller frame to a larger frame. The larger frame, I've got more beef in there, you know, more metal, more stronger springs to hold those contacts closed for those higher fault currents so that I can do that. And then what I can do is I can adjust my long time pickup, you know, that portion that's, you know, what I should do is, I can't do that. I don't have my green screen. I'm in my kitchen right now. So I move I can move my long time pickup down. Now here's the problem. That 150 amp breaker is not on the same equipment. It's not like it's a main. What's connecting that 150 amp breaker to that bar, you know, where the 20 amp breaker is a conductor. In fact, it's 150 amps worth of conductor based upon conditions of use. So here's the issue that you run into. You beef up that breaker, you put a 400 amp frame breaker, or maybe a 600 amp frame breaker, or I mean an 800 amp frame breaker, and you dial it down, but you might not be able to dial it down to 150 amps. So what do you got to do? You need to put a larger conductor. And then if you put, I don't know, say you have to put 250. And you got 250 amps worth of conductor, because that's the lowest you can dial that larger frame breaker down to. Now you're feeding the equipment, which used to be a 150 amp panel. Now you got to put in a 400 amp panel, whatever that new number is, or a 250 amp panel, right? So you now have increased the size of the infrastructure. And why is that? Is it because you have more load? No, it's just because you need those contacts to stay closed for those high fault currents. So that's the challenge when you start to try to address selective coordination and putting larger devices upstream. I'm going to answer your question, Mr. Garcia. Give me a second. And I'll answer yours too. Atir. All right, so I love this. I love this discussion. So let's just finish this process out. So I can address selective coordination by making the upstream device larger. What does that do? It may cause me to increase the conductor size. It may cause me to increase my downstream equipment size. And also, not every circuit breaker fits in every panel board. Right? So I might even have to increase the size of the panel board upstream to accommodate, instead of a 150 amp multi-case circuit breaker, maybe a 400 amp frame or an 800 amp frame circuit breaker that's adjusted down. So the new breaker the new frame I get into might not fit in that upstream panel board. All of this. And this is why you got to do it in the design phase. I tell engineers this all the freaking time. If you don't do it right in the design phase, so here's what happens. Well, I'll get to that later too. Anyway, okay, so you got the upstream device that you're going to try to adjust. You're going to make it larger. The other thing you can do is reduce the fault current. Now, so remember, the fault current on is 5,000 amps. I want to get it down below to 1,500 amps. One way I could do that, put a 1-to-1 transformer, isolation transformer in the picture. Now, that big hunk of iron core is going to knock that fault current way down. It does a couple things for you. Reduces incident energy for you. Could reduce incident energy if you get your fault current less than 2,000 amps. If you get your available fault current less than 2,000 amps, IEEE 1584 tells us the likelihood of that arc sustaining itself is less. And I would almost argue it's not going to sustain itself. The amount of energy is too low. So if I can knock it down below 2,000 amps of bolted fault current value, I meet my selective coordination for these two breakers. I've added a transformer though. So that's another problem. And what that does is that makes me put another breaker as a main instead of a main lug only panel. And then you get to the coordination through a transformer, which is another video that I did. Stuff. Love it. Anyway, So I can increase the upstream overcurrent device's size, and I can still use the tables, or I can reduce the fault current by putting a transformer in, or tell your electrician take a few laps around the block with his conductor, right? Go down 4 floors, come up 7 floors, and come back down 3 floors, and you're golden. You just added a ton of copper, and you can reduce the fault currents. And then your third option is that BAB20, that's downstream, the red curve. You can take that and replace it with a fuse. Because now what you're doing is you want to increase the speed of the downstream to device. So I can put a fuse, a 20 amp fuse downstream of this F150, and that fuse is going to act so fast that that breaker is not even going to know an event occurred. If you're at 5,000 amps, you're in the well into the current limiting region of a 20 amp fuse. I think that's 20 amps. Yeah, 20 amp fuse or 30 amps. And you're going to clear within less than a quarter of a cycle. That F150 upstream is just going to be like, it's going to blink and go, whoa, what was that? I don't know. What the heck was that? It's going to sit there with its contacts closed. I don't know what that was. Why? Because the downstream device goes so fast. So you got 3 options. Increase the upstream overcurrent device, which adds complications, increases the conductor, possibly increase the upstream panel board. You might have to increase the downstream panel board. And then it's it also increases fault current. Or you can put a 1-to-1 transformer to reduce the fault current, or you can make the downstream device go faster. And if it's a breaker solution, I don't know that there's any other breaker faster than that BAB20. But if you had, I don't know, if you had like an insulated case, you can try to put a molded case downstream, but then you get, so in any case, you just want the downstream device to go faster. So those are your options to get this to selectively coordinate. And it's just an intriguing. Okay, so let's take a look. All right, Ryan Jackson in the house. A tier. If, and this is coming in on LinkedIn, a tier, get over there and subscribe to my YouTube channel, buddy. You got to get over there. And if you're already subscribed, I love you. If you're not, please, then I will love you even more. Remember, subscribe. All right. It's just a plug. Anyway, if the AHJ only requires coordination up to 0.01 seconds, then the tables need not be consulted. If it's 0.01 seconds, you don't give a crap about fault current. You're not doing anything for fault current. 0.01 seconds has absolutely nothing to do with available fault current. You're ignoring fault current. Everything you know about engineering fundamentals, everything you know about reality, everything you know about how circuit breakers operate and how they function, you take all of that, you put it into a cup, or no, not into a cup because I want to drink that. You wrap it up into a napkin, you roll it up like this, and you throw it away. Because 0.01 seconds has nothing to do with fault current. Will both of those probably trip on ground fault currents, the most common fault in the power distribution system? Heck yeah. Will they trip on a bolted short circuit current? Absolutely they will. The only thing they won't trip on is an overload. Now, what you do for 0.01 seconds, you have to plot the trip curves. And you've got to just basically hide everything below 0.1 seconds. You don't even want to look at it because it'll make you sick if you know what you're doing. You hide everything below there. This curve right here, 0.1 seconds, works fine. If your fault current was 5,000 amps, put it this way. If your bolted fault current for this pair of breakers was 5,000 amps, you know, and you had a bolted fault, you know they both open. If a ground fault let's say they say ground fault currents are around 60 some percent or whatever. If you look at the IEEE books, your ground fault currents say around 60, 70% of the bolted three-phase bolted fault current. To make it easy, let's just say the ground fault current is 50% of the bolted fault current, which makes that 5,000 amps, 2,500 amps of ground fault current, the most common fault in a power distribution system. Your coordinated system for a ground fault will cause multiple devices to open. Done deal. It could cause your main overcurrent protected device to trip and take the entire facility out. Why? Because you did 0.1 seconds. So yes, you are right. You don't need the tables. You don't need you don't even need to calculate fault current anywhere in the system other than to do interrupting ratings. All you need to do is look at the overload region, hide everything below 0.1 seconds, and make sure you have separation of curves. That's all it is. It's art. It's like art. That's all it is. Piece of cake. All right, and Jay Garcia, are the selective coordination tables good for the short time region as well? If there is overlap in the instantaneous and short region, would the tables work for both regions? Oh, good question. All right. The answer to that question is the tables are only applicable when the fault currents are greater than both of the instantaneous values. It has nothing to do with long time curves or short time curves. If you have an overlap in those regions, that does not selectively coordinate. It doesn't even coordinate at 0.1 seconds. And you not only you may say, I just used the tables, go away, leave me alone. If you do that, you definitely will have a problem because you have to adjust your long time pickups, your short time pickups, your short time delays, your long time delays. All of that has to look good on the curve. They have to have separation all the ways down, except for when you get the fault currents up into when the fault current is greater than the instantaneous on both sides, like these two curves. If that red curve encroached in and overlapped with the blue curve in that long time, short time, long time delay region, it will not selectively coordinate. It won't even coordinate to 0.1 seconds. You just can't use the tables and leave everything else alone. You've got to plot the curves, unless you're using fuses. Fuses, you maintain a 2-to-1 ratio. You don't have to plot the curves. You don't need to know the fault current. You're maintaining a 2-to-1 ratio. Whatever the ratio says, most often it's 2-to-1. You might, depending upon the fuses that you're using, you might have different ratios, different, 4-to-1 ratio or whatever. But most commonly is a 2-to-1 ratio. If I've got a 20 amp fuse downstream, I can use a 40 amp or greater upstream. Up to 200,000 amps. I don't care. I don't need to plot any curves. That'll work over the full, because there's no adjustability on a fuse, right? Circuit breakers have adjustability. And even though these two circuit breakers don't have adjustability, you still got to plot them because you got to make sure that the overload regions and anything else doesn't overlap with each other. Great question. That's probably a very valid question. So here's the problem that you have sometimes. You'll get to where you don't get questions, right? But they're very valid because people might have just done that. They say, well, I just used the tables. That's like zone selective interlocking. Oh my gosh. I had one guy in the audience. I was teaching a class and he goes, he says, I just lost my train of thought, but he goes in the back, he goes, oh, I know what I do. He says, I just use zone selective interlocking. He goes, I don't worry about any of this because I zone selective interlock my system. And I said, you CSI, I mean, you run wires between circuit breakers. He goes, oh yeah, even outside for downstream, because I zone selective interlock. He said, I don't worry about any of the settings on the breakers. I was like, well, A, you're spending a lot of money to zone selective interlocking, especially outside. I don't know anybody who's done that, who does that. But B, zone selective interlocking doesn't get you selective coordination. And it was like, we had a good hour discussion, and I had to draw it on the screen, help them understand zone selective interlocking has nothing to do with selective coordination. And he finally got it and understood it. But and then there was the oh crap moment, right? Because you think about all those projects that you did. But anyway, all right. So let's go down through. Does the put up? Are the selective coordination tables? Greetings, Tom and all. Are the selective coordination tables good for short regions? Okay, that was Mr. Garcia. Robert from Omaha in the house. Thanks for joining. William Snyder, Willie. Does the NEC require the conductors to be larger if the OCPD can be dialed to 150? Ooh, good question. The only time you would have to go larger is if you can't lock the cover. So remember in 240.4, I'm going by memory. Look at that, Kevin Arnold calling me. I'm going to have to call you back, brother. In 240, they tell you that if you can lock the cover, then you can set whatever your setting is can be that for that conductor. So that's actually a very good comment. The challenge, Willie, is if you can't lower that low enough. So if like in the case of this one here, I've got say a 150 amp panel downstream, or say a 200 amp panel downstream. If I increase the upstream overcurrent device size large enough and I can't dial it down, then I'm changing out a panel if I've already installed it. But to your point, if I dial it down, I lock the cover. Now I'm into I think it's 240.4D. Man, I don't know. It's 240. I think it's 240.44. Man, I don't know. Oh wait, I got no. Am I working on? Yeah, I am right here. So I got link up on my iPad. 240. I'm gonna see how far off I was. What's 240.4? 240.4 is protection of conductors. D. No, it wasn't D. Man, that is wrong. 240 standard ampere ratings, 240.6. See? 240.6 adjustable trip breakers. The rating of the adjustable trip circuit breaker having external means shall be maximum setting possible. Local restricted access, C. A circuit breaker that has restricted access to the adjusting means shall be permitted to have an ampere rating that is equal to the adjusted current setting, the long time pickup. Restricted access shall be achieved. So if I put that cover, lock it, I can locate it behind removable or sealable covers, located behind bolted equipment enclosed doors, located behind locked doors accessible only to qualified personnel. So if I take that room and I lock the room, make an electrical room out of it, and I lock it, only accessible, then I meet that requirement. And then password protection, because some of those electronic trip units have passwords on them. So, but great question from Mr. Snyder. Already did that, man. You're the man. Thank you, sir. Stan Spence, but adding the fuse solution, doesn't that add inspection requirements, thus more new risks? I don't know, Stan. What new inspection requirements for a fuse that you would do outside of a breaker? I mean, if I put a fuse in, you might say, well, you have to make sure that somebody didn't put, the different size or different type fuse in there. But I could say, make sure that the dials are on my circuit breaker too. I've seen dials change mysteriously. Nobody touched them, but all of a sudden, my short time pickup and my instantaneous and my long time delays are all changed. And it just so happens it was on a motor load, but. Yeah, no, I don't understand. I don't think that there's any additional inspection requirements for a fuse. I would say go to NFPA 70B as in Bob, and take a look at the maintenance intervals and whatnot. I'd say there's less maintenance on a fuse for those reasons. I don't think there's a. And here's another thing, Stan, I would say on especially on some of these circuit breaker solutions, here's what I see. What inspector is looking at the settings on a trip unit? Think about this. I'm the customer. I pay my. Now we have services to do this for you. Okay, we can come out and we can do all of this. Eaton has an engineering services division that'll smoke anybody else in the industry. And we'll come out to the facility. We will do your short circuit study, do your coordination study. We will go to every one of those trip units and make sure they're all set. But there's no inspector there's David Williams, Michigan. He looks at them. He'll call me and say, hey, Tom, he'll send me a picture of a trip unit. I'm looking for the long time pickup. If David's out there, I know some inspectors do it. I know many inspectors, they'll say, that's not their job. That's not what they do. And then when you look at the trades, who is actually setting them? Is IBW out there setting them? Are our electricians out there looking at studies and setting them? I think you should pay them to do that. I don't think anybody's doing that. Good question, though, Stan. Thanks for the responses. Already subbed to the channel. You're the man. Here. You mentioned putting a 1-to-1 transformer or increasing the cable lengths to reduce fault current. Would that have an impact on voltage drop across the conductors? Wouldn't that need to be considered as well? And yes, it should. That's what I'm saying. These solutions are not easy. If I get a 1-to-1 transformer, I might be able to put taps in, So here's, so a tier, very good question. So here's the thing. Schindler, I think it's Schindler. What do you call it? Elevator control panels. We put a code change into the National Electrical Code that said you had to mark the elevator control panel with available fault current. And what did that do? It raised the awareness that elevator control panels have a very low short circuit current rating. But in cities like Seattle, Pittsburgh, Pennsylvania, just 20 minutes from my house. New York City, okay? In these high-rise buildings, what do we use to get power from floor to floor to floor to floor to floor? Busway. Busway. You know what Busway is? Busway is a high-efficiency fault deliverable system. High-efficiency, H-E, fault, H-E-F, delivery, D, H-E-F-D-S. It's an H-E-F-D-S. Felix Sandoval, he put an acronym for it to me. It's a high-efficiency fault deliverable system. And then what happens is you've got 200,000 amps or 150,000 amps at the bottom of the building. You got about 20-some thousand amps or 30-some thousand amps at the top of the building, and you've got a elevator control panel rated for 5 or 10,000 amps if you're lucky. 10,000 amps if you're lucky. I think typically it's like 5. So Schindler, I believe it was one of those. I don't know if it was Schindler, Otis, or one of them, but they actually had a catalog number. So I had a guy call me from Seattle, Washington, trying to fix the problem of the available fault current on the roof. And he said, what do I do, Tom? I said, if the elevator control panel, all you do is all you need to do is a UL 508A analysis. And you probably can do an analysis, maybe change a couple components and get 65K easily. And we proved it. We did it. We did it for one of the industrial control panel manufacturers and for elevators specifically. And he says, I said, but call the elevator control. I call Otis or Schindler or whatever it was. So he did. He said, you know what I got to do, Tom? He calls me back. Guess what? He goes, they're going to sell me a transformer 1-to-1 that I'm going to put up on the roof. And he had the same question that you had, Atir, about voltage drop. He knocked the fault current down. Then he had to put an overcurrent protective device to protect the transformer. And you can't just, on the secondary, you have to protect the secondary. It's a wide grounded system. And go look at 240, go look at 450, go look at 408, all that good stuff. you need to put a secondary main on that. So it just got complicated really quick when all that they have to do is increase the short circuit current rating. But very good point, Atir. I think I got your name right, Atir. Hopefully I'm saying it right. But thank you. A very good point. Imagine, if you will, two air circuit breaker curves without any overlapping regions. Do we still need to have some grading time between two instantaneous regions? Wait a second. Without any overlapping regions. Mateus, if you have two air circuit breakers without any overlapping regions and they both have instantaneous goes down. So I don't know how you wouldn't have overlapping regions unless the fault current is less than the instantaneous of the upstream device. Like, for example, on these two curves, imagine, if you will, that these are two air circuit breakers, and let's say that red device doesn't come all the way down. It has just a short time delay. And let's say that the available fault current is less than where the blue curve comes down. I don't need to do anything else. I selectively coordinate. I got separation. I'm good to go. But if the instantaneous is, the instantaneous can overlap, as long as here's what happens. Oh man, I'm trying to think of how do I say this. And I'm not downstairs where I can bring up a whiteboard. So how do I do this? Oh, wait a second. I think I know how to do this. Let's try something. I am going to try something. Oh man, I tell you what, if this works, I am a technology freaking guru if this works. I'm just testing. And if this works, I'm telling you what. OBS, FaceTime, Double Eagle 2. Oh my gosh. Does it? Double Eagle 2. Okay. Let me do this. Let me do transform. Fit to screen. Nope. Is this Double Eagle 2? I think that's Double Eagle 2. FaceTime, Thomas's iPad. OMG. Oh my gosh. I'll tell you what. Technology. You know what? I was not, in years past, I was not an Apple fan. But I'm telling you what I'm doing right now is because of Apple. So if Apple's out there, I think how do I do this? I think they need to send me a new iPad and new technologies and all that good stuff. All right, so let's do this. And you know what I'm using? I'm using Notability. I think it's Notability. I think it is, yes. All right, so here's I'm just going to do this. So there's one breaker, and here is another breaker. If these are my power circuit breakers, right? So these are, say, power circuit breakers. I don't have an instantaneous, good to go, obviously. And let's say that, now, what I'm trying to say is sometimes the software will cut these curves off at the available fault current. And sometimes they don't. All right. So, and the reason I say that, let's say that you did this. Let's erase all of that. Let's say that I had a downstream circuit breaker and I had an upstream circuit breaker. And you say, well, look, I've got overlap of curves right here. But if my fault current is right here, if you don't set your software to cut the curves off, and I do not like when those software applications, so I specifically turn that off because I want control over what is on the screen. Sometimes I'll get something that cuts it off, like right in here. All of this is like missing, and I'm just not a fan of that at all. So if your fault current is less than the instantaneous region of the upstream device, you're good. You can have overlap just in the curves, but the fault current is less than the instantaneous pickup. You're golden. If I'm trying to think of, all insulated case circuit breakers are going to have a what do you call it, instantaneous. So your question was, imagine two air circuit breaker curves without any overlapping regions. Do we still need to have some grading time between two instantaneous regions? If, like I say, if that's the only, I don't know how you don't have overlap of instantaneous. Only if the fault current is less than the upstream breaker. And if it's less than the upstream, if it's less, like for example, if your fault current is here, okay, and let's say that it cuts off the, let's say it cuts off the downstream breaker like that, right? So let's say that your downstream breaker is cut off and there's a space in between those two. And there's a space in between those two, then is there, and this is another question you get on selective coordination, is how much space do you need in between curves? And that is purely an engineering decision. That's your comfort level. I've seen people butt these puppies right up against each other. I have seen some, like my mentor, when I was working at Gilbert Commonwealth out in Reading, Pennsylvania, he wanted a specific amount of space in between all of his curves. And that was fine. I think, in my opinion, that's engineering judgment. There's nothing that I could find in books that tells you what that space needs to be. All right. Hopefully, Mateus, I hope I answered your question. I hope. Hey, I love these Q&As. Excellent. Thanks for listening during lunch. I was a little bit late this morning. In fact, I wasn't even going to go. I was working on something else, and I'm like, you know what? I got to do my Q&A Friday. So I appreciate the feedback. Imagine two air circuit breaker curves without any overlapping regions. Well, you asked the same question twice. All right, that's good. 240.6c. Yep, Mateus, between two air circuit breaker curves without overlapping regions, do we need some grading time between two instantaneous regions? For example, between two relays, we should allow for 200 to 250 milliseconds. All right, so you're getting to the separation in between, and you're looking at 200 to 250 milliseconds. So, and when you say milliseconds, you're talking time. So that means that you're talking like, and you specifically mentioned relays. So when I think of a relay curve, right, you're looking at something like sort of like this. If it's a CO type of relay or whatnot, you might have something like this. And this is one relay, and this is another relay. It's not a band, because relay curves. I don't typically see bands on relay curves. That's another good point. What do we do? When we do relays, we never really see a band. Like when I used to do the Westinghouse CO relays and stuff like that. Now, on the new relays, like our Digitrip, oh my gosh, IQ 1002, which is a motor protection relay, IQ 1000, IQ 1002, the DP 4000 was a meter. The FP5000, that's a feeder protection relay. Those did have bands. But when you go back in time, the old relays didn't have bands. They were just straight lines. So you had to have the tolerance. But what you're saying is you're looking at milliseconds. So you're looking at how many milliseconds in between those. And yes, I would agree that you've got to take into consideration the I gotta get back to my thing here. Hold on. There it is. You got to take into consideration the bands, which on some of those relays they don't have. The newer relays they do. And then even between when you have bands, then there's the question of how much time do you put in between the curves, and that all is. So your 200 to 250 milliseconds. Mateus, I think, is what I've seen, but I don't know that is in an IEEE document. In fact, you know what I'm gonna do? I'm gonna go to the Red Book real quick. I am going to go to the Red Book. And if you guys and gals out there don't know what the Red Book is, you go to IEEE has a series of color books. The Red Book, and that now they're doing like the 3000 series, right? That it's now the 3000 series. I got to go to my power systems engineer. I think I go to master files. I haven't moved all those files up. Professional engineer. And I have my color books in IEEE color books. All right, so I'm gonna go to the Red Book. No, I'm gonna go to the Buff Book. Buff Book is on selective coordination. And that's like the, geez, oh man, the Buff Book. Here we go. What edition? To 1996. I'll go to the 2001 edition. I'm going to do 250 milliseconds. Because I do remember that number. I'm not finding 250 milliseconds. If anybody knows if there is an IEEE reference on the space to leave between those two, I've always just thought it was sort of like an engineering rule of thumb recommendation. 250 milliseconds sounds about what I used to use for space, but I'm not finding it as a reference in the Buff Book. So anyway, I'd like to know. So the thing I think of, Mateus, is whenever I would do something, like if I did a coordination study and a short circuit, I always put my assumptions. So what I used to do for selective coordination before it was in the code, I used to use the most common fault in a power distribution system, which was the ground faults or the arcing faults. I believe it was the Red Book would say the most common fault in a power distribution system is the arcing fault, and I would plot the three-phase bolted fault, and if I didn't coordinate at that value, then I would, and most of the time, outside of nuclear, most of the time I'm doing like a commercial building, I would put a note that you're not required to, but I would say you don't coordinate at the bolted fault, and I would determine whether or not they would coordinate to the arcing, the most common fault in the power distribution system, which is your arcing ground fault. And if they coordinated to that, I would say, look, I would just tell the customer that you don't selectively coordinate at the bolted fault, but you do coordinate at the most common fault in the power distribution system, which is the arcing ground fault. And I would state the IEEE reference on why I thought it was the most common fault. And then what I would do is I would say, if you wanted to coordinate at that most common fault, here's what you would change. I always just honed in on the most common fault you see in a power distribution system, which is that arcing ground fault. And then the NEC for Article 700, 701, 708 added selectively coordinated for all currents. That brings in the bolted fault current. In some complex systems, it can be challenging to meet the recommended time gaps from IEEE 242. All right, so there is that time gaps in 242. 242, let's see. Is that, Yeah, that's the red book, or that's the buff book. All right, so that is out of the buff book. I should have just read your next note. Have you always been able to meet the recommended time gaps? In the past, I have. So now here, remember now, like when I was in my heyday, I never had a problem with the gaps, and that's why I know that 200 to 250 looked familiar. It's been a while, and that's out of 242, which is the buff book for all of you people out there who are not familiar with the IEEE color books. But the jobs that I did, I didn't have any problem. Now that's not everything, right? So I had exposure to nuclear Crystal River Unit 3, which was a nuclear application. I had exposure to a commercial plant. One was an Alcoa plant. The other one was a Union Carbide plant. So a couple of those, I mean, I was instrumental on. I also did some military base stuff, not military bases, but military installations. I was Army Corps of Engineers. I did, and now I did an Army Corps of Engineer job, and I said, I need the one line. They said, can't send it to you. It's classified. I said, okay, well, I need to know the available fault currents, so I need the study. Can't send it to you. It's classified. I'm like, okay, then can somebody at least draw out on a piece of paper just the overcurrent, something that's not classified? They said it can't. It's classified. So how am I supposed to do a study? Anyway, that was a nightmare job. I don't even want to talk about it. Christopher Fink. I would recommend one talks to other electricians about simply turning up the settings. We do it a lot. See, that's my point, Chris. That's my point. No matter what, I don't care if it's a fuse or a circuit breaker. You know, fuses, I've seen people put the wrong fuses in. I've seen people have different catalog numbers in A, B, and C, all that jazz. But I've seen so many breakers either not have their settings set. And here's what happens, Chris. Nobody sets does the settings and establishes the settings on installation to even match a selective coordination study, which they probably paid a massive amount of money for. So nobody changed the settings. The settings are typically shipped at the minimum. And what happens is you start a motor, it trips the breaker. And then what do? You turn the dial. And then not only don't you have your coordination from the get-go, now you're messing with dials. And God only knows if they changed the right dial. Hey, Steve Froming. Hey now, must show fought. Problem is good luck trying to find the actual control panels. Oh, okay. Steve Froming, finding the actual control panel. This is the elevator controls. I just glue the cover for the dial shut. Willie Snyder, don't glue the shutters, man. If you're on the bottom floor, you blow up. In the middle floor, you burn up. On the top floor, you're okay. I gotta remember that one. That's a good one. All right, Willie Snyder, that's one way. Okay. Jay Garcia, instantaneous. You got the point when you with the word band. There it is, Mateus. I don't know what 2GB means. I don't know. You're Mateus. Your post looks really cool. It's like highlighted in blue for me. I don't know what that means, but that's kind of cool. Relays need 0.2 millisecond separation, but breakers do not. Just need daylight. So Jake Garcia, yeah, you're right. So that's what I've heard. But I worked under a PE, really great guy, taught me a lot. He actually had like a little, we used a ruler in between circuit breakers itself. But relays, yeah, they're treated a little differently. And then fuses, you got to be careful with fuses because some of the fuse curves are just an average melt, and you need a minimum clear and a maximum clear. Maximum melt. Minimum, maximum. It's a min-max. I don't know. I can't remember anyway. Jay Garcia, TK, thanks. I'm going to hit close. Mateus, distribution uses different times than transmission. Delay depends on your application. For industrial distribution, 0.2 milliseconds is usually used. Yes, I believe. And I believe I can fly. So I would, I love that buff book. If you are into coordination, if you just want to learn something, here's what I like about the buff book, the IEEE 242. Which we call the buff book. What I love about the buff book and the red book, which I think is 141, let's just double check. IEEE 141 is the red book. The green book is 142. That's on grounding. The gray book, that's commercial buildings, I think, 241. You got the buff book. You got the brown book, which is on studies. Don't get that one. That one's hard to read. Orange book's on reliability. I wouldn't get that one either because it's so freaking old. The gold book, I can't remember what the gold book's on. Let me open it. Hold on. Gold book. Oh, reliability. Reliable system design. Violet book, that's a decent book. That's calculating short circuit currents in your industrial. That's relatively new. That's like in the 2000s. The white book is on healthcare. The blue book is on circuit breakers. The emerald book, if you get into, now we're into an IEEE book discussion. The emerald book is a good book for, I used the emerald book a lot when I was doing the security system for Crystal River Unit 3 in understanding shielding for frequency and because we were doing communications, and this is a long time ago, I learned that you ground the shield on one side, not both sides of those conductors. But the Emerald book is a great reference for power quality stuff, and grounding of electronic equipment. That's a really good book. I love the color books. I still love the color books. They're moving them to 3000 dot standards, which I don't know if I'm buying that one. But anyway, Steve roaming in the house. I meant must show photo of trip settings to put in the file. Excellent, Steve. I did not know that. That is good to know. That's a good point. That's a good one. Boy, that's a lot of breakers you got to take pictures of. Aren't the color books being phased out, Dan? Yeah, they are. They're going to 3000 dot standards. So here was the problem they had with the color books, which I didn't find it as a problem. I sort of liked it. If you look at the buff book, which is 242, and you look at 141, the red book, both books have a chapter on calculating fault currents. Some people would say they want one book on calculating fault currents, and they want to take it out of the buff book and the red book to be consistent. And then in the red book, you got various applications of where they overlap. So what the 3000 dot standards are supposed to do is get rid of the overlap, the redundancy in content. And I get it. That's fine. But I just love the color books, and I liked the different perspectives. I would read the buff book on fault current calculations, and I read the red book on fault current calculations. Both of them had a little bit different information, but the same gist. It wasn't that they conflicted with each other. They were saying the same thing, but in a different way, and it helped me understand it. Is there a case when the sensors do not match the frame on the, when you say MCB, molded case circuit breaker? If sensors are lower than the frame, the instantaneous setting will be different. That's correct. Yeah, you got to look at the sensors. You do have to look at the sensors, because I believe the trip curves will run off of the sensor. If you have different sensors put in, the trip curves are adjusted accordingly. That's why you really got to look at the trip curves of circuit breakers to make sure that you are, there's the trip curve itself on a circuit breaker or for a relay, whatever it is like another technical document. It gives you a lot of really good information that is important for the proper application. So I think if I were, that's just that's a gimme. You got to read the trip curves and even all the details with regard to adjustment factors and whatnot. Would be wise to consider positive percent tolerance on top of the expected tripping times for protective devices that have been in service for many years. Walter Gonzalez, wow, that's profound, buddy. And we're that, so that is that's an interesting perspective, because when I get into this discussion, when we start teaching NFPA 70E, and we talk about incident energy, and we talk about 70B maintenance and maintaining circuit breakers, the problem I have with adding additional time, how much time do you add? Where do you get the number from? Is it based on, and you got to be careful, right? So I have my PE license. Walter, you might have yours too. I picture myself on the stand, and they say, so Mr. Dimitrovich, you added half a millisecond or whatever on your curves outside of what the manufacturer proposed. Yes, I did. And apparently that wasn't enough, because this was not maintained and the incident energy was way higher. It took that breaker a lot longer to open. Where did you get your numbers from? Well, I got those from the book of Thomas Dimitrovich. It wasn't enough, was it? No. Do you really know what you're doing, Tom? And I could go down that road, and all of a sudden now I'm guilty because I added a fudge factor of some sort, maybe for coordination and maybe for arc flash. Let's say it was for coordination, and it wasn't enough because they didn't maintain the breaker. And the trip curve took a little bit longer, but I put in a few milliseconds more, but it was more. So I don't know where you get that number from. I don't know how you justify what that number is outside of what the manufacturer says. And then what you do in your study is you say, look, this is based upon a maintained system. If the manufacturer says, look, you maintain the circuit breakers and these trip curves are going to perform that way, then and then you do your maintenance, and if you follow NFPA 70B, which requires you to verify a few points every now and then you shouldn't add any time. It's okay to be careful, but that's my only concern, Walter, about doing anything that is not based upon standards. Is whenever whatever it is you're doing, if it's because the book of Tom or the book of Walter Gonzalez, then I think you run risk. You accept risk because now you've established something. And if you weren't quite right, then you need to justify why you weren't right. Now, if it's conservative, okay, well, then maybe you have less risk, right? But you've really got to look on a case-by-case basis. Do NFPA standards 101, 110, and 111 somehow work in concert, or is it important for them to be separate standards? I would say a lot of these work in concert with each other. Outside of 110, 111, etc., 70, 70B, and 70E, they relate with each other. 70 relates to 110. 70 will say, look, you need Article 700 says you need a backup generator. And then you go to 110 about the performance requirements for the fuel and all that other good stuff. So they all relate to each other. In my opinion, and that's Willie. I thought that was Walter. In my opinion, Willie, I think that we can't look at a system from a standards perspective, book at a time. It's a system. There are a lot of codes and standards that all interrelate with each other. So I believe they do, and that would be a good program to explain why. Does the judge accept fudge? Yes. And just no money. No money should exchange hands. But fudge could exchange hands, right? Maybe a bottle of Ardbeg or Lefroy. I don't know. We do not condone nor accept bribes on this channel. All right. I think I've been going for just about an hour. And I don't know why my iPad says 9:41 a.m. January 9th. But it does. And I think it's just the browser. So I don't know what's going on. But in any case, all right. So I think great discussion. I really enjoyed the discussion around selective coordination today. Great questions. I really enjoyed that. MCB is molded case circuit breakers, molded case breakers. MCCB, yep, excellent. All right. I still would like to know, Mateus, how you got that highlighted around there. That's kind of cool. I love it. All righty. Well, Mr. Froming. So, Steve, you know, Bobby Joe, my wife did not like the black background either. Hey, happy Labor Day. Happy Labor. You know, I'm taking the week off next week. So it's kind of cool. We're going to have fun. We're going to see the world. Happy Labor Day. Walter Gonzalez, it depends, comes into play. Yes, excellent, Walter. Excellent. And thank you for joining in. Thanks, everybody, for joining in. Willie, Jay Garcia, Mateus. Oh, wow. You are the man. I didn't know what that was. That's kind of cool. I really appreciate it. I thought it was like 2 gigabytes. I'm like, okay, I don't know what the heck that means. I'm from the UK. You are the man. I really appreciate you. Oh gosh. You know what? You just bought me a beer. I appreciate it. Now I got to go figure out what 2 gigabytes mean. Well, happy Labor Day. Excellent. All right, everybody. Thank you for joining in. I really appreciate it. I had a great. I love doing. When I was doing studies, I really enjoyed studies. So short circuit study, coordination studies, and I dabbled in arc flash studies. I didn't do those as much as I did the others, but it's all related. So thank you for joining in, and hopefully we learned something together. So silly stuff and easily overcome. All righty. Happy Labor Day. Thank you, Mr. Garcia. Take care, everybody. Please stay safe this weekend. No, don't drink too much. Don't talk too much. You can always talk. Talking's good. Sharing information, always good. Just take it easy, right? Stay safe. Stay healthy. Turn off your phone next week. You know what, Chris? And Bobby Joe is going to make me do that. That's going to be tough. I've got to record my IAEI news live for Tuesday. I got to do it today because tomorrow we're going to be gone. I'm going to be so busy next week. It's all about Bobby Joe next week. So we're going to have a lot of fun. So, and the 2 dogs. Jake gets his stitches out tomorrow, or his staples. His torn ACL, we get the staples out tomorrow, and then we're going to have fun. So we're going to take off. All right. I got to see my ending here. Thanks, everybody. Take care. Stay safe, please. You know it. Stay healthy. All right. Have a good one. I'm going to sign out. Bye-bye.